Hey folks, this is probably going to be kind of a long video, so you can feel free to skip around. It's 4 example problems. The first two are about work being done by a single force. The third one is work being done by the net force, and then the fourth one is a power problem. So use this one as much as you need to get started on any problems. So the first one is calculating the work done by tension. If the tension force is 18 newtons and directed at 40 degrees above the horizontal, pulling a sled for 2 meters. So, it's simple drawing time for Mr. McIntyre here. Here's the sled, here's the string, and here's Mr. McIntyre pulling it. And so that's the generic, that's what's happening to the sled. As far as a diagram of this is concerned, this is not a free body diagram by any sense, but the problem names a specific force that kind of excuses you from doing a free body diagram. But what you want to understand is that even though tension is the force you're being asked about, other forces can be doing work on the sled. And so this actually, the answer to this problem doesn't completely inform what's going to happen to the sled. In other words, its speed is probably going to increase, but it might not if there's a strong enough friction force. So what the kind of visual is there's a force of tension at an angle. Now, when the sled gets pulled, the sled moves a certain distance, and then there is an angle between those two vectors. And so, the sled moves along the surface of the snow, and the angle of 40 degrees is given relative to the horizontal. So it's given relative to the snow itself. So that angle of 40 degrees, in addition to being the angle that the force is projected upward, is also the angle between the force and the displacement. So we can use that as our theta when we solve for FD cosine theta. Okay, so the work done by tension is just going to be the force of tension times that distance times the angle. So it's just, basically taking the numbers that I gave you and putting them in the equation, but also understanding that 40 degrees is both above the horizontal and the angle between the force and the displacement. So we would just say 18 newtons times 2 meters times the cosine of 40 degrees, and that's equal to 27.6 joules. So, if tension were the only force acting in part in the horizontal direction, then the kinetic energy of the sled would increase by 27.6 joules. What we haven't talked about is friction. And so if there's a friction force, and depending on how big it would subtract from this energy. And so kind of the overall gain in energy of the sled is not going to be 27.6 joules. It will be less because friction will remove some energy from the system while the tension is adding it to the system. Next one is purposely a little odd, work done by gravity while lifting a tray of food a certain distance in the air. So gravity can do work even if it's not the thing that causes action. The work done by gravity on the sled in this problem is going to be 0 because the sled is moving in that direction and the force of gravity is straight down. This is an angle of 90 degrees, and the cosine of 90 degrees is equal to 0. So the work done by gravity on the sled is 0. Conceptually speaking, there's nothing about the force of gravity that has a chance in changing the energy of the sled. It's on the ground, gravity is pulling it that way, so it can't do anything. However, while an object is being raised or lowered, gravity is capable of doing work. And so I can calculate the force of gravity. So gravity does work with the force of gravity, and that's great. I can plug in the mass of the food tray and our value of little g, and I would get a force of 9.32 newtons. So gravity is exerting a constant 9.32 Newton force on this food tray while it's being lifted. The work being done by gravity is going to be that 9.32 newtons times 0.60 meters. And then I have to think about the cosine of what angle. So, back to drawing a picture. The food tray is going to move vertically upward, and at the same time, gravity is going to act vertically downward. This angle is 180 degrees. So gravity is pushing against the raising of the tray. So 180 degrees. Cosine of 180 degrees is -1, and that's really important. And so the work done by gravity is negative 5.59 joules. Gravity, as the tray is being lifted, is removing energy from the system. If we think of gravity as external to the system, it exerts its own net force. As I lift it and add energy to the tray, gravity takes that energy away. An alternative assessment to that is you are actually storing 5.59 joules of energy in gravity. And so gravity can do work. If it's part of your system, then that energy stays in the system. If it's not, then the energy leaves that system. Another thing to think about, this is the work done by gravity. If you take something that's like here, and then you lift it up to here, gravity does negative work on it because the object is moving in the opposite direction as gravity points. But think about what's happening because of your hand. If you lift something with your hand, you're pushing up on it. Whatever you want to call that force, you can call it a normal force, an applied force. You're pushing in the same direction that the object is moving. So you're doing positive work. That positive work in this situation has to be equal to positive 5.59 joules. The reason we know that is because if I start here, the object starts not moving. And if I push up and then stop, the object is also not moving. And so if I consider the work done by the net force, that has to be 0 because the kinetic energy of this object didn't change. So the work done by gravity has to actually cancel the work that I would do with my hand. More on that during class. Number 3, final speed of a 1,500 kilogram car going 15 meters per second if the brakes do negative 1,000 joules of work on it. So we had learned this idea of work equals a change in kinetic energy. In your equation sheet, it says delta E equals W equals FD cosine theta. So we will work on like how to use that in class, kind of over and over again. But this is one way to do it. That work done by the net force causes a change in kinetic energy. We can now substitute some things because we know that kinetic energy is 1/2 mv squared. We can substitute. And with energy problems, it's critical that you understand kind of at what level of detail your numbers belong. In other words, the brakes do negative 100,000 joules of work. That is equal to the work done. You don't need to worry about FD cosine theta. That's just the work is negative 100,000 joules. On the other hand, you have mass and speed, and so you want to substitute in the 1/2 mv squared into this equation. So 1,500 and then 15 meters per second, and that's squared. So, because k equals 1/2 mv squared, and I have the mass, one of the speeds, and I want the other speed, I have to substitute 1/2 mv squared for my k. So this is the equation that I end up having to solve. That's negative 100,000. I should calculate this, add it to negative 100,000. I'll get a positive number, multiply by 2, divide by 1,500, take the square root, and I get that the speed is 9.6 meters per second. So part of this problem is showing you how to set up a work energy question. The other part of it is showing you that you can take 100,000 joules of energy out of a car and its speed has just decreased, in this case, by 5.4 meters per second, or like 12 miles per hour. So that's like a ton of energy from what we've seen in our problems, but it's really not that much in terms of a car. Last problem for this video is a power question, and this is like one of the most complex power questions that is available. So the ones in the sheet should be easier than this. So average power delivered by a Prius engine as it accelerates from rest to 8.3 meters per second in 9.25 seconds if an 8 Newton drag force acts. So this is like, there's a lot going on here. The power equation, it's work or change in energy divided by time. There are lots of ways to solve this problem, and here is the way that I went about doing it. Basically, if I know the force, the distance, the time, and the angle, I can calculate the power. So I will fill this equation in later. I have a lot of work to do so far. The only thing I don't really have to do work for is the 9.25 seconds is going to go right there. This is average power. It's accelerating, so the speed is going to increase at a regular interval. I can use the FV cosine theta for power, but I would need to find the average speed, which it's up to you whether you want to do that. So because this is power delivered by the engine and there's a drag force, I need to do like a force analysis here. So I'm going to start with Newton's second law. And we'll say like, okay, so the engine is going to provide maybe like a positive force and the drag is going to be a negative force. So we'll say that the force of the engine minus the force of drag is equal to mass times acceleration. Now, the definition of acceleration is change in velocity over change in time. And because I have numbers that relate to that in my problem, I'm going to write acceleration as this. I could use a kinematics equation to find acceleration. I'm just going to use that symbolically. And so I have, to fill this in, the force of the engine minus 8 newtons equals 1,400 kilograms. The change in velocity is going to be 8.3 meters per second. So it's going to be from 0 to 8.3. Let me move that up so you can see it all. Divided by the 9.25 seconds. And so I have to solve this because, you know, the force of the engine is not equal to the net force. I have to take away 8 newtons from the engine's force to get the net force. I need to put that in there. And so my force of the engine is going to be 1,264 newtons. So that's the constant force delivered by the engine, or average force, to cause this acceleration. So that's kind of like, that takes care of the F way up here. And then I have the time, and then the D is what I'm going to find next. So next is going to be finding D. Let me get that in the screen. There we go. To find D, I'm going to use this equation. And so I have to find something first to do this. So this, like x and x naught, that's essentially d. The v naught times time is 0, so d equals 1/2 a t squared. And so I'm going to find that acceleration right now. I'm going to do it inside this equation. So the distance I need to find is equal to 1/2. Acceleration again is delta v over delta t. So I'm going to again put this 8.3 meters per second over 9.25 seconds. And then the time is 9.25 seconds, and that gets squared. And if you like look at this, it essentially amounted to the speed times the time in that situation, and it's half the speed times the time. So this is 1/2 times the acceleration times the time, and I have a distance of 38.5 meters. Cool. Okay, so I now have all the numbers I need for plugging in to this equation. So I go back up to my power equation. I put in my net force, or not my net force, my engine force to 1264 newtons. I put my distance, 38.5 meters. It's going to be the cosine of 0 because the engine, the engine just spins. But basically, I'm kind of like uh, glossing over that bit right now and saying that the engine is going to cause a force that's in the same direction that the Prius is going to accelerate, and then 9.25 seconds in my denominator. So I divide all that out, and I get 5,261. I forgot to do this in the video for power. The unit for power is the watt, which is a capital W. So 5,261 watts is the power. So I hope you got some useful tidbits out of this video, and we'll go over more in class.